Okay, today we're going to start 8.1 with our exponential functions. An exponential function is a function where the variable is in the exponent. These are just some key features here that you can read on your own. The most important one that I want to point out is that it will always go through the point 0, 1. You could take any number and put it to the 0 power, that will always be 1. So for each of these graphs, we will be passing through the point 0, 1. You will be permitted a calculator. We're just going to grab some points and get them on the graph. So we're looking to graph a function here, 2 to the power of x. We're just going to pick some values of x and make a t-table for ourselves here. So like I said before, anything to the 0 power is 1. If I let x be 1, 2 to the first power would be 2. If I let x be 2, 2 to the second power would be 4. And if I picked a negative 1, that negative flips around the fraction, so we'd be at 1/2. 1, 2, 3, 4. There we go. So your basic exponential functions, and I'm only going to really require 2 points out of you guys. I want to see the point 0, 1, then one other point on the graph. And you should know if the base is an absolute value greater than 1, it should be an increasing value. Now if you look at the constants here, to multiply 1/2 by 2, if I multiply by 2, I get 1. Multiply by 2 again, I get 2. Multiply by 2 again, I get 4. So if we give you a list of values like we are here and here, you should be able to tell if it's exponential or not if you're multiplying by the same value each time. To turn 2 into a 5 through multiplication, I would have to multiply by 5 over 2. To turn 5 into 8, I'd have to multiply by 8 over 5. These here are already not the same value, so the answer here is this data exponential, and the answer to the question would be no. In order to multiply something to 2/3 to get 1, you would multiply by 3 over 2. Same thing here, multiplying by 3 over 2, and this pattern repeats. Since I'm multiplying by the same value each time, this is exponential, and the answer here would be yes. Okay, so let's just do a little bit more graphing here. All of these exponential functions transform just like all the other ones. A coefficient out front can make it grow, it can make it shrink. If we had a negative out front here, that would be a reflection over the x-axis. A is going to stand for our base. We have our minus h and our plus k. The h is a horizontal shift left and right. The k is a vertical shift up and down. So when I look at this equation here, what would this look like? It would move the entire function 1 unit to the left. Remember, that's a minus h in there, so it's moving it in the opposite direction. So where our normal point of 0, 1 would be there, we're going to move it 1 point to the left. This guy here, for number 2, this guy would translate 3 units to the right and 2 units up. So there's a couple of ways you can graph these guys. You can kind of just think about it transformationally. I'll show you this one time here. If I took out the transformation parts here and here, a function would be 4x. If I made a little t-chart for the original values, I let x be 0, we get 1, x be 1, we would get 4. So I'd be here, and here in green would be our original points. In purple, I'm going to do the transformation. We're moving 2 units to the right and 3 units up. So I'd move 1, 2, 1, 2, 3, 1, 2 to the right, up 1, 2, 3. Normally we have an asymptote sitting on the x-axis, but this plus 3 is going to move that up to here. And our graph would look like this. So that's one way to graph these transformationally. If you do not like that, you can just pick some values for x and plug it in. Pick your values wisely. I'm going to pick 2 because I know 2 minus 2 is 0, and anything to the 0 power is 1. So 4 to the 0 power would be 1, plus 3 would get us 4. And you can see we moved it transformationally, we got to that point, or you can just plug in your values. I could pick 3 for an x value. So 3 minus 2 would be 1, 4 to the first power is 4, plus 3 we get 7, and you can see at 3, 7 we also have a point here. I usually just plug the values in, it's a little bit easier for me than doing the transformations, but you should be able to, if we give you an equation, tell us how it transformed just by looking at it. For example, number 3, the negative is going to make this guy do a reflection upside down. This plus 1 is going to move that horizontal asymptote up 1. Since the normal exponential graph goes this way, a reflection is going to be going this way, so it's going to look like a decreasing function. So I'm just going to pick some values out here. So let's say we picked 0, right? So I let 0 go in here. Anything to the 0 power is 1. 1 plus 1 is 2. If I pick 1, we're going to have negative 4 plus 1, which would get us negative 3. Oh boy, that moved up 1. Oh, it'd be negative, I'm sorry, this guy here would be negative 1 plus 1. This guy would be a 0. I'm just kind of looking. This would be here, making our function go like this here. Let me just explain that problem. It's really minus 1 times 4 to the 0 power plus 1. And I made a common mistake. 4 to the 0 power is 1 times a negative 1. And that's where that 0 is coming from. My apologies, guys. All right, let's flip our papers over. These are kind of running the same way. You do need to realize that if the base is an absolute value less than 1, it is also going to be working like a decreasing function. We're just going to pick some x values and see what we get. We did not transform left or right. We're really concerned with the ones up and down, so our horizontal asymptote stays in the same place. If I let x be 0, anything to the 0 power is 1. If I let x be 1, the y value would be 1/2, so we can see that we are decreasing. And just to make sure, I'm going to let x equal negative 1. Remember, a negative exponent is going to flip the base of that power over, so we would get a positive 2. So that's getting me a good look at what this graph should look like. I'm just going to show you something here. You don't need to do this. We can just go and pick values. But this here can really be written as 4 times negative 1 to the x power. That negative 1 is going to take the base and flip the fraction over. So we're going to have 1/4 to the x power. So I can see that the base here is really a value that is less than 1, absolute value less than 1. This guy's also going to be working like a decreasing function. So we're going to make our basic little t-chart here with the xy. If I let x be 0, and again, it did not transform up or down, so we're keeping our asymptote here. If I let x be 0, anything to the 0 power would be 1. If I let x be 1, that's going to get us negative 1, so that's going to get us 1/4. So it is decreasing like it should. And if I picked negative 1, that would turn out to be 4 to the positive 1 power, so that would be 4. And this guy's coming down, decreasing like this as well. Same thing here. I see this negative exponent, so I know that it's going to be a decreasing power. I just picked some points. I'm just going to write them here for time purposes. I have 1, 3, 0, 5, negative 1, 11. So negative 1, 11 would be way up here. 0, 5 would be here. 1, 3 would be here. I do see this plus 2 moving that horizontal asymptote up, again creating a decreasing function. Okay, so I'm just going to talk about the number e for a little bit. turns out to be 2.718. There is an E button on your calculator, so it's sitting in blue right above the division sign. As n approaches infinity and you keep putting values in for n, you can see it starts to approach this number. For our purposes today, you just need to know that e is a number and not a variable. As we move into logarithms, we will eventually see that e and a natural log will cancel each other out. But for today, you just need to know that e is a variable. All right, so we're going to solve some basic equations here. What you want to make sure is that you have bases that are the same, and then you can set your exponents equal to each other. You will always, not always, but most likely take the bigger number and try to change that into a power. So over here, I got 3 to the x plus 2. Well, 27 is the same thing as 3 to the third power. Now that the bases are the same, we can set the exponents equal to each other. And I see that x is equal to 1. All right, looking at problem number 8, again, when I look at these bases, that e is not a variable. It is the number e, that 2.718 approximately. We're going to have to do a little work on this side to get down to 1 power. We need to combine them up the exponents. Not going to do anything to the left. When you raise a power to a power, you multiply the exponent. So this is going to be e to the 3x. And if I want to write the second part here, 1 over e squared, as not a fraction, I want to write it as a fraction, I could write this with a negative exponent. Now we have 2 powers being multiplied. And when we multiply our powers, we add our exponents. This is going to be e to the 3x minus 2. Now that we have a common base of e, we can set the exponents equal to each other to solve. This is looking like a quadratic, so we want to set everything equal to 0. This is factorable. So we can have minus 2 minus 1. So we get x is equal to 2 and x is equal to 1. All right, that is all for today. We will pick up next time with 8.2.